Hello everyone. So today is our second lecture. So before I start this lecture, I just want to point out a few things after the first lecture that I've realized. So first things first, looks like keeping the time duration of 1.5 hours is not really a good idea because it seems that I am running faster than a normal class. So what I have decided to do instead is that I will take lectures topic wise. Okay, so I would have decided how much content I want to cover in one particular lecture, and depending on that I would be making the video. So if it takes less than 90 minutes, be it. If it takes more than 90 minutes, bear with me. Okay, so that is the first thing. And second thing is, so schedule is like, I promise that I would be giving lectures on Tuesdays and Thursdays, but this Thursday I could not upload the video. So just bear with me, but in the same week you should receive 2 videos. Okay, and as soon as I upload a video, I would be posting a message on Moodle so that you'll be informed about it. Okay, so if at all I am cancelling a lecture or rescheduling it, I would definitely let you guys know. But unless I inform you of any such thing, lecture is very much scheduled and it should come in that week itself. Next is, I received a few suggestions that my voice was a little lower in the previous video. So this time I'm trying to talk louder. I mean, of course, if I stop this recording in between and try to listen to figure out how I am sounding, it interrupts the video. So I can listen to my own voice only when it's available for you also. And recording the entire lecture again is not really possible. So I'm speaking louder in this video. Let's see how it comes out. And yeah, we have the lectures pretty much topic wise. Okay, so let's start with this lecture. And also some people asked me if I can tell them how I plan to cover the topics. So initially we would be linearly covering the book which I mentioned as the first reference, which is Using the Borsuk-Ulam theorem, written by Chennai Mathematical. And after that we will shift to the Kozlov's book on combinatorial algebra and topology. Okay, so in the first lecture we have covered its first chapter. Today I am starting the second chapter, and plan is to cover the first section of this chapter. Okay, and in the next week we will cover the rest of this chapter. Okay, so please do let me know again if you find my pace faster, but for now let's just start with the lecture. Okay, so the main topic today is the Borsuk-Ulam theorem. You might have seen or heard about many variants of it. Okay, and there are many equivalent versions, there are many different proofs for this theorem, there are many extensions, generalizations, and of course many applications. And one of the most beautiful applications, which at least I found the most beautiful, is in the area of combinatorics, and that is why the course is named as Topological Combinatorics. We will see how Borsuk-Ulam theorem has given such a beautiful proof to a purely combinatorial problem. Okay, so that is where we are heading ultimately. And to start with, there are several proofs for this Borsuk-Ulam theorem, several versions. In today's lecture we will see some 4 or 5 versions and see that all of them are equivalent. We will give quick proofs for those, and that is it. But let's see what it really tells you intuitively. Okay, so what it really says is that if you have a continuous mapping from Sn to Rn, maybe I should write bigger and thicker also. So this pen certainly gives me a thick lining, and let's see if I can write bigger also. So you have Borsuk-Ulam theorem. In the most natural form, it says that every continuous mapping from Sn to Rn, you have a point x in Sn such that f of x and f of minus x are mapped to the same point. Okay? So, x and minus x, we all know they are called the antipodal points because you are working in the Sn. So, what it really says that any continuous mapping, if you take from Sn to Rn, then you have a pair of antipodal points going to the same point in Rn. This, in rough senses, also means that, let's say if you are standing on a globe, okay, of course globe is not Sn, but we all know that it is homeomorphic to Sn. So using that homeomorphism, we can just consider it to be Sn. And I say that if, let's say I am taking a temperature function, which means at each point of the sphere of our globe, I associate with it the temperature it has. Okay, so every point on the globe will have a temperature for sure. Then this is saying that, and having a temperature, you know that it's a continuous function. You can't have in a very small neighborhood some portion to be very hot and some portion to be very cold, right? It's a continuous function. So what this is really telling me is that there are diametrically opposite points whose temperature is going to be same. Okay, and through pictures also it is given in this book. So let me just show that picture also to you. So if you start with a ball like this, okay, and you flatten it, what it is saying is that there were a point of antipodal points, a pair of antipodal points, one here and one exactly behind it, that when you crumble and flatten it, they are now lying on top of each other. Yeah? Which means when you have flattened it and you have sort of brought it into Rn in some way, in a continuous fashion, then these points are one over another. And this is the, one second. So let us now start seeing what are the equivalent versions for the Borsuk-Ulam theorem, and this we are going to see in the most general form, which means we are going to state all of these statements for any n possible. Okay, so let me first list out the different versions and then we will see their equivalences. First we will have all of them in the terms of mappings, and then we will have them in terms of covers, open covers and closed covers. Okay, so let me state the first version, Bu 1a, as in Borsuk-Ulam first version, which states that okay, so all this I'm going to do for every n non-negative, that every continuous mapping f from Sn to Rn, there exists a point x in Sn, basically the one which I just stated, such that f of x is same as f of minus x, which means antipodal points, there is a pair of antipodal points which is being mapped to the same point under this continuous mapping. Okay, the second version is in terms of the antipodal mapping, which means f of minus x is minus of fx. For every antipodal mapping f from Sn to Rn, there exists a point in Sn such that its value is 0. Okay, just let me mention, antipodal means that for every x in Sn, f of minus x should be same as minus of fx. This is visible. Okay, so f of minus x we want to be same as minus of fx, and if this happens for a continuous mapping, that is called an antipodal mapping. So this is the second version. Third version is, third version is in some sort of like negations. So 2a is that there does not exist antipodal mapping from Sn to Sn minus 1. So you cannot have an antipodal mapping if you reduce the dimension by 1. Okay, and in the same league there is one more version which says that there does not exist any continuous mapping f from Bn to Sn minus 1 which is antipodal. On boundary of Bn. Okay, which means you have that f of minus x is not equal to minus of fx for every x in boundary of Bn. Right? Antipodal would have meant that f of minus x is minus of fx. Antipodal would have meant that f of minus x is minus of fx for every point on the boundary, but the negation is that you do not have any such mapping, so f of minus x is not equal to minus of fx. So there is at least one point which does not satisfy f of minus x is same as minus of fx. Okay, so let me first give equivalences of these with each other, and then we will see two more versions of the Borsuk-Ulam theorem and we will prove the equivalence with them. Okay. So let's start with the BU1A implying BU1B. So recall that BU1A means that for every continuous mapping f from Sn to Rn, there is a point whose antipodal point also maps to the same point, whereas BU1B implies that for every antipodal mapping there is a point which is mapped to 0. Okay, so here if you see that if I assume this and assume the antipodal mapping, it just tells me that there is a pair of antipodal points which goes to the same point, right? So that just tells me that there exists an x in Sn such that f of x is same as f of minus x, but in our case f is antipodal. So I know that f of minus x is minus of fx. Okay, so having this put here, I have f of x to be same as minus of f of x, which tells me that f of x is 0, and this is done. Okay, now let's see how BU1b implies BU1a. So if you assume that you are given an antipodal mapping and you have to show for the continuous mapping that it is going to map at least one pair of antipodal points to the same map, just consider this map g of x being defined from Sn to Rn as g of x to be f of x minus f of minus x. Okay, so first of all, just check what is g of minus x. So g of minus x is going to be f of minus x minus f of x. This is actually minus of g of x, correct? So g is antipodal, right? So therefore by BU1b, what I know is that there exists an x in Sn such that g of x is 0, correct? But g of x is equal to 0 implies that f of x is equal to f of minus x. So therefore there exists an x, this particular x you have already produced. There exists, so for this x, therefore for this x in Sn, f of x is equal to f of minus x, and this is what is being demanded in BU1a. Okay, so with this we have proved that first two versions of the Borsuk-Ulam theorem are equivalent. We now will shift to the next two versions. So just recall, the versions that we are going to see now are this and this. So 1b states that for every antipodal mapping there is a point which is mapped to 0, and BU2a implies that there is no antipodal mapping from Sn to Sn minus 1. Okay, so let's start with BU1b implying BU2a. So if you have an antipodal mapping, so suppose you have an antipodal mapping from Sn to Sn minus 1, okay, then you can also consider this as an antipodal mapping from Sn to Rn, right? Because Sn minus 1 is embedded inside Rn. And by BU1b, what I know that there exists a point x such that f of x is 0. So by BU1b, I know that there exists an x in Sn such that f of x is 0. right? But f of x is equal to 0 it cannot be a point in Sn minus 1, whereas this is the same f, which implies that, so basically this gives you a contradiction, okay? So there does not exist any antipodal mapping from Sn to Sn minus 1. Okay? Now, if I look at the converse of this, so Bu2A implying Bu1P, so I have to start with an antipodal mapping and I have to produce a point x for which the value is 0. Okay? So, suppose you have a continuous nowhere 0 antipodal mapping. So, on contrary, what could happen that there exists a map from Sn to Rn, okay, which is antipodal, continuous, and f of x is not 0 for any x in Sn. Okay, in such a case, what you can do is you can define a map G from Sn to Sn minus 1. How you're going to define? You define it as g of x to be f of x divided by norm of f of x. Why I can divide? Because I know that f of x is nowhere 0. Okay? So, this is a well-defined continuous function, and what it gives me, that it is an antipodal mapping. How? You can just check. So, what will be g of minus x? This is going to be f of minus x upon norm of f of minus x. Correct? And f we know is an antipodal mapping. So this is minus of f of x, and inside norm minus is not going to make a difference, so this remains norm of f of x. So this actually turns out to be minus of gx. So this gives me that g from Sn to Sn minus 1 is an antipodal mapping. Which contradicts my Bu2A. Okay, therefore you cannot have a non-vanishing antipodal continuous map from Sn to Rn. And with this, we have now shown that these two versions are also equivalent. Okay? So for the remaining part, let's first see the projection map that we have of the upper hemisphere with the lower dimensional ball. So clearly see, if you have a circle which is S1 and you look at this upper hemisphere and just project it down on this R1, then this is a homeomorphism, right? So if I let this map phi, so of course this similar thing you can do for any Sn. Okay, you take its upper hemisphere, so let's say upper of Sn, and then you bring it down to Bn. This is possible, right? So this is what I'm going to do here. So you send it from upper of Sn to Bn. What it really is as a map, you take all n plus 1 coordinates of Sn and you project it down on the first n many elements. So this is how you get the Bn. You just chop off the curved thing and what you get is the projection. Okay, so this is a homeomorphism. You can check this for yourself. Clearly this is a homeomorphism. And now if you have an antipodal mapping F, so if there exists an antipodal mapping F from Sn to Sn minus 1, remember what was BA, BU2B and BU2A were? Let me just show again. So 2A says that there is no antipodal mapping from Sn to Sn minus 1, whereas BA2B says that there is no continuous mapping from Bn to Sn minus 1 which is antipodal on the boundary of Bn. This is N2. Okay, so right now I want to see that what would this imply. So if you have an antipodal mapping like this, then this also gives me a map from this to this which is antipodal on the boundary of this map. Okay, so I am doing it by contrapositive. So what we are really saying is that any antipodal map from Sn to Sn minus 1, antipodal gives a map from Bn to Sn minus 1 which is antipodal for sure. Additionally, it is antipodal on the boundary of this, and this is going to contradict my BU to B. Okay, so and if at all you want to see it through this in technical terms, this is nothing but the map Gx which is being defined as f of pi inverse of x. Okay, you take any point on this Bn, you take its image on the boundary and apply f to it. Okay, since it's an antipodal mapping, once I know what happens on half of the hemisphere, I know what has to happen on the rest of the half, correct? Because f of minus x is defined in terms of f of x. F of x has to be equal to minus of f of x. So once I know the value f of x, I know what happens on f of minus x. Okay, so defining it on just half of it suffices. Okay, and conversely what happens is that if you have any g, okay, if you have any g from Bn to Sn minus 1 which is antipodal on the boundary of Bn, okay, we can define f from my Sn to Sn minus 1 as f of x to be g of pi of x. So what it's really doing, you take the elements, you project them down, and then you apply the antipodal map of the boundary which you have got here. Okay, and this specifies f on whole of Sn for the same reason that it's antipodal on the equator of Sn. So therefore the resulting f which you have defined here, this is continuous, and it's continuous on both the hemispheres, right? On the upper hemisphere as well as the lower hemisphere. Therefore f is continuous on whole of Sn, and this is going to give you an antipodal mapping from Sn to Sn minus 1, which is a contradiction. So with this we now also know that Bu to A is equivalent to Bu to B. Okay, so these were the versions of Borsuk-Ulam theorem in terms of mappings. First, so we had two in the sense of just the continuous mappings, and two in the sense of non-existence of so one in the sense of existence of continuous mapping having certain property, and then one was restriction of a continuous mapping having such a some particular property. One was in the sense of antipodal mapping having a property, and the last one was no antipodal mapping existing having a certain property. There are two more versions that I'm going to list out here. Excuse me. So, LSC, I will tell you shortly why it's in this format. What it says is for any cover F1, F2, Fn plus 1 of an Sn by n plus 1 closed sets. Okay, so I'm considering a cover of Sn by n plus 1 many closed sets. If you have this, then there exists at least one Fi containing a pair of antipodal points. Okay, so usually what it really says is that if, let's say, I have taken S1 and I take two closed covers which forms its two closed sets that which covers this S1. Let's say I take the upper hemisphere and I take the lower hemisphere. Then in this particular case, actually both of these contains these two antipodal points. There could have been other choices, like let's say I take this as one of my closed set. Okay, and so let me just number these so that it's clear which one I'm referring to. This is for my second cover. This is one set, and another set possibly is this. Okay, so this is one open closed set, and this is another closed set. So it covers my S1, but in this case you can clearly see that this particular section, which is this, contains many pairs of antipodal points, not just one. Okay, and this is precisely what this is saying, that even if you go in a higher dimension, if you take any Sn and you take the number of sets in the collection to be one extra, you are guaranteed that at least one closed set is going to contain a pair of antipodal points, and that is why this C is here. C for the closed sets, LS because this formulation was given by Listernik, Schinrelman. So let me just write this down. Okay, and they gave another version which is LSO. So by now all the topologists have already figured out what this O would be once you know what C is here, and that precisely is the reason. Now we will talk about open cover. Okay, for any cover U1, U2, Un plus 1 of Sn by n plus 1 many open sets, there exists at least one Ui which contains a pair of antipodal points. Okay. So to see the equivalence of these statements with the previous ones, let's just first see equivalence of LSC with the BU2A. So just recall, BU2A means that there is no antipodal mapping from Sn to Sn minus 1, and this says that if you try to cover Sn by n plus 1 many closed sets, then at least one set is going to contain a pair of antipodal points. Okay, so we will first see the equivalence of these two sets. So, or rather, BA1A implying LSC. Okay, so let's say you have chosen a closed cover. Okay, let F1 up to Fn plus 1 be a closed cover of Sn. Define a function from Sn to Rn which sends any point in Xn to the distance of X from the first set, distance of X from the second set, and so on up till distance of X from the nth set. Right? So this is a vector in Rn. Now what does BU1A tells you? That every continuous, and of course you can check that this is a continuous mapping. So any continuous mapping by BU1A has a point X in Sn such that f of X is same as f of minus X. Correct? So let's say this point is some y. Now possibilities are that this y, which is a vector in Rn, either all of its coordinates are non-zero or at least one of the coordinates of y is 0. So if let's say if ith coordinate of y is 0, that means distance of X from Fi is 0, right? Also I know that f of minus X is also same as y, that means distance of minus X from Fi is also 0. But recall that Fi's are closed sets, so having distance equal to 0 implies that these points belongs to the set. So this would imply that X and minus X belongs to Fi. Okay, and if no coordinate of y is 0, in such a case what I know is that this particular X which I started with does not belong to any of these points, any of these closed sets. But recall that F1 to Fn plus 1, they are forming a cover of Sn, which means every point belongs to at least one set. So this would imply that x belongs to fn plus 1. Correct? But f of x is same as f of minus x. So f of x equal to f of minus x implies minus x also belongs to fn plus 1, and therefore x and minus x both will belong to fn plus 1. Okay, so you know that if at all you have a closed cover of Sn by n plus 1 many sets, then there is at least one set among these which contains a pair of antipodal points. Okay, and by now we already know that Bu1a is equivalent to Bu1b, Bu2a, Bu2b. So for the reverse thing, I am going to check LS of C implying Bu2a, because I know that Bu2a is equivalent to Bu1a. Okay, for this, first let's observe one thing, that if at all, so this I know that whenever you try to cover your Sn by n plus 1 many points, you have a pair of antipodal points coming in one set. But if you allow one more set to come, so if or rather there exists a covering of Sn minus 1 by n plus 1 many closed sets, such that no set contains a pair of antipodal points. Okay, so to see this quickly, so remember the simplex definition which I gave in the previous class. So now what I'm going to do is I'm going to look at a 2 simplex. Remember what was a 2 simplex? It was a convex hull of convex hull of 3 affinely independent points. So in R2, in R2 I can take this, right, convex hull of this piece. Okay, and now if you take these as your closed sets, this line segment is one closed set, this line segment is one closed set, and this line segment is another closed set. Everybody agrees that this is homeomorphic to S1, and here I have 3 closed sets. So S1 is being covered by 3 closed sets, and clearly none of these, if you want to project, you can take this projection. Okay, just push things out, and then these shows you that you have this cover of S1 by 3 closed sets, none of them containing a pair of antipodal points. Okay, so having this in place, if you have a continuous so if there exists a continuous antipodal mapping, if there exists an antipodal mapping, f from Sn to Sn minus 1, recall we are trying to show that LSC implies Bu2a. Bu2a was that there is no antipodal mapping from Sn to Sn minus 1. So I'm doing by contradiction, that if at all there is an antipodal mapping from Sn to Sn minus 1, then you choose this with this particular collection of closed sets Fi's that we just generated in the previous page, or rather let's say F1, F2, Fn plus 1, okay, and then take the inverse image. So then you're going to get F inverse of F1, F inverse of F2, and so on, F inverse of Fn plus 1, right? Recall that F is continuous, so this closed implies F inverse of Fi's are also closed, and this is forming a cover here, so these sets form a cover of Sn. So this gives you a cover of Sn by n plus 1 many closed sets, and none of them contains an antipodal point. So then these forms a cover of Sn by n plus 1 closed sets, and no set having a pair of antipodal points. And this contradicts the my LSC. Okay, so with this now I also know that LSC is equivalent to all the previous versions. Okay, now what is left is the LSO. So for the LSO, we are going to see its equivalence directly with LSC. So starting with LSC implying LSO. Okay. So to see this last bit, this direction is pretty clear, right? That if you take any cover of Sn by n plus 1 many open sets, so let u1, u2, un plus 1 form an open cover of Sn, then you can choose Fi's such that Fi's are contained in Ui's and Fi's are closed. Okay, and how you know that such a set exists, and that you take for every point of a set, okay, you take an open neighborhood whose closure is contained in some Ui. Okay, and then by the compactness I will be able to form a finite collection of these sets, and I will get these Fi's that are closed, and then I know that at least one Fi contains a pair of antipodal points. That will give me there is that Ui which contains a pair of antipodal points. For the reverse direction, let's use some visualization. So for this, what you do is that you assume the contrary. So if at all So now you have a collection of closed sets which is forming a cover of Sn. So if f1 f2 fn plus 1 cover Sn, each fi is closed, then what you do is that, so if no fi contains a pair of antipodal no fi contains a pair of antipodal point, contains x and minus x, then it specifically tells me that the each fi is closed and every 2 points of it have distance strictly smaller than 2, right? Because if the distance becomes 2, then I am actually looking at a pair of antipodal points, right? So for any 2 points, one second. So as I was saying that if you assume that f1 f2 fn plus 1 forms an closed cover of Sn and each fi is closed such that no fi contains a pair of antipodal points, then notice that you are actually saying that given any 2 points their distance is less than 2, right? So and for any x and y in fi, distance of x and y is strictly less than 2, correct? Now with this condition, what you do is that you look at the open set formed as follows. For each fi you define ui to be the set of all those points in Sn whose distance from fi is less than this epsilon by 2, let's say, okay, where epsilon is the smallest distance that you could have chosen. So in such a case, what happens is that each of these ui's altogether forms an open cover for Sn, but none of the ui contains a pair of antipodal points, which is going to contradict ls0. Okay, so with this it completes the last bit, that LSC is equivalent to LSO. Okay, so we saw 6 equivalent versions of the Borsuk-Ulam theorem. Okay, so today's lecture I will end here, and now for the Brouwer's fixed point theorem, I encourage you guys to look at it and see how that is related to the Borsuk-Ulam theorem that we did today. And secondly, what is remaining is that in throughout this book we will see various proof techniques, okay, sometimes using geometry, sometimes using some other techniques of combinatorics, sometimes we'll have degree theoretic proofs. All of these will come one after another and we'll be doing them as we go along. In the next lecture I would be covering the next section of this book, of this chapter, which is a geometric proof for the Borsuk-Ulam theorem. Okay, so this is it. Hopefully in the next week we will finish this chapter, and please let me know if my pace is still fast, as some of you told me for the last lecture, and if the audio quality is better this time, video quality is better this time, or if it is still hazy or blurry, please do let me know. Please write back to me. Okay, thank you.